Find somewhere comfortable. You don't need to sit up straight or hold yourself in any particular way. If you're already lying down, stay exactly as you are. Pull whatever warmth you have a little closer and let your eyes do whatever feels natural. Close, if they want to. You don't need to follow any of this carefully. You don't need to remember a single word. Tonight we're going to travel somewhere very old, somewhere so ancient that the word old barely reaches it. We're going to think about mountains. How they come into being over millions of years, how they slowly, quietly pass away, and what it means that they are always, in some sense, doing both at once. It's a big story. And we have all the time in the world. If today was hard, and for many people, today was hard in ways that are difficult to name, then this is a good place to rest. You don't have to do anything with what you hear. You don't have to form opinions or arrive at conclusions. Just let the words move through you, like wind moving through a high valley, touching everything and disturbing nothing. The mountains have been here long before any of us arrived. They will be here in some form long after. And for now, in the dark and the quiet, we can simply be near them. Settle a little more deeply into wherever you are. The day is already behind you. What's ahead is only rest. There is something that happens when you stand at the base of a very large mountain. Something that is hard to describe, but that almost everyone has felt. The ordinary scale of things stops working. The mountain is simply too big for the measuring tools you carry inside you. Your eyes try to find the summit, and the effort itself feels like a kind of surrender. You become, for a moment, very small. And strangely, that smallness is not unpleasant. It is almost a relief. People have felt this for as long as there have been people. Mountains appear in the oldest stories we have, as homes of gods, as the edges of the world, as places where the ordinary rules of human life thin out and something older takes over. The Greeks placed their gods on Olympus. The Hindus considered the Himalayas to be the dwelling place of Shiva. The Hindus considered the Himalayas to be the dwelling place of Shiva. The Hindus considered the 4 sacred mountains that define the boundaries of Dinabikaya, the homeland. Across cultures and centuries, something about mountains has made them feel like more than geography. They feel like presences. And in a way, they are. What most of us don't fully sit with. What we tend not to think about because it's so large it slides off the mind is that the mountain you're imagining right now, whatever mountain you're picturing, was made. Not built by human hands, but made, assembled over millions of years by forces so enormous and so patient that they operate entirely outside of human experience. The mountain did not simply appear. It grew. Slowly. In the way that all deep and lasting things grow, quietly and under enormous pressure. There is something interesting in that, if you let it arrive gently. The things that endure are the things that form slowly. To understand how a mountain is born, you have to go back further than the mountain itself. You have to go down. Beneath the ground you're lying above right now, beneath the soil and the bedrock and the deep foundations, the earth is not solid all the way through. It is layered like an enormous and very old piece of fruit. The outermost layer, the crust we live on, is relatively thin. Under the continents, it reaches perhaps 70 kilometers at its deepest. Under the ocean floors, it is thinner still, sometimes only 5 or 6 kilometers from the seafloor to the mantle below, and below the crust, the mantle. A vast region of rock so hot that it flows very slowly, like the thickest imaginable syrup left in a warm room. This flowing of the mantle is what moves the world. The heat driving all of this comes partly from the original formation of the Earth 4.5 billion years ago, when the planet was assembled from colliding debris, and the violence of that assembly is still slowly bleeding away. It comes also from the radioactive decay of elements deep inside the planet. Uranium, thorium, potassium, quietly releasing energy in the dark. The Earth is, in a sense, still cooling from its own birth. And as it cools, it stirs. The stirring creates what are called convection currents. Hotter material rises, cooler material sinks, and the whole mantle circulates in enormous, unhurried loops. And floating on top of all that movement are the tectonic plates. Great slabs of crust and upper mantle, some carrying continents, some carrying ocean floors, all of them drifting, very slowly, across the surface of the Earth. Slowly is perhaps an understatement. The plates move at roughly the same rate that your fingernails grow, somewhere between 2 and 10 centimeters a year, depending on which plate you're looking at. The Pacific plate moves a little faster. The Eurasian plate is more leisurely, but given enough time. And geology has nothing but time. Even that gentle drift becomes something extraordinary. The man who first argued seriously for this idea was a German meteorologist named Alfred Wegener. He published his theory of continental drift in 1912, and the response from the scientific community was, to put it kindly, cool. The established geologists of the day found his evidence intriguing, but his mechanism unconvincing. They could see that the continents looked as though they might once have fitted together. The eastern bulge of South America slotting neatly into the western concavity of Africa, as if torn apart along some ancient seam. But they could not accept that continents moved. The Earth, they insisted, was essentially fixed. Wegener spent the rest of his life defending his theory. He died in 1930 on an expedition to Greenland, still largely dismissed by the scientific mainstream. It would take another 3 decades before the evidence became undeniable. That evidence came, quietly and patiently, from the ocean floor. In the early 1950s, a young cartographer named Marie Tharp was working at Columbia University, helping to map the floor of the Atlantic Ocean using data gathered by research ships. The work was painstaking and largely invisible. Tharp was, for a time, not permitted on the research vessels herself, because the ships were considered no place for women. She worked from the data others brought back to her, translating columns of numbers into the shape of an unseen world. What she found hidden in those numbers was a mountain range. A vast, continuous ridge running down the center of the Atlantic Ocean, thousands of kilometers long, with a deep valley running along its spine. When she showed her findings to her colleague, Bruce Heason, he initially dismissed them. The valley at the center of the ridge, Tharp suggested, was a rift, a place where the ocean floor was being pulled apart. Heason called it girl talk. But the data kept accumulating, and the picture kept sharpening, and eventually the conclusion became unavoidable. The sea floor was spreading. New crust was being created at the mid-ocean ridges, welling up from the mantle below, pushing the old crust outward and apart. And if the ocean floor was growing, then the continents on either side of it were moving. Wegener had been right. By the late 1960s, the theory of plate tectonics had been accepted by the scientific community. It is one of the great unifying ideas in the history of science, a framework that explains earthquakes, volcanoes, the shape of continents, the distribution of fossils, and, of course, the birth of mountains. The plates are always moving. Right now, as you rest, they are moving. Somewhere on Earth, two of them are drifting toward each other, and the slow collision is already beginning to fold the crust. The mountain that will rise from that collision will not have a name for millions of years, but its birth has already started, in the dark, under unimaginable pressure, in perfect silence. When two tectonic plates collide, something has to give. The question is, what exactly gives? And that depends on what the plates are made of. The ocean floor is dense and heavy. It is made of a dark, iron-rich rock called basalt, and its weight means that when it meets a lighter continental plate at a boundary, it tends to slide downward, diving beneath the continent in a process called subduction. This is not a fast process. It is not a dramatic one in any human sense of the word. It is simply relentless. The ocean plate descends into the mantle at an angle, grinding downward over millions of years, and as it goes deeper it heats up and begins to release water and other volatile elements into the mantle above it. That water lowers the melting point of the mantle rock and magma forms. The magma rises, and where it reaches the surface, volcanoes grow. This is how the Andes were made. The Nazca Plate, a section of ocean floor beneath the Pacific, has been sliding beneath the western edge of South America for tens of millions of years. The result is the longest continental mountain range on Earth, over 7,000 kilometers of peaks and valleys and high plateaus running like a spine down the entire length of the continent, the volcanic peaks of the Andes. Aconcagua, Cotopaxi, Chimborazo. But there is another kind of collision, and it produces something different and in some ways even more extraordinary. When two continental plates meet, neither one wants to go down. Continental crust is lighter and more buoyant than oceanic crust, and it resists subduction. So when two continents collide, there is nowhere for the material to go except up. The crust buckles. It thickens, it folds, like a cloth pushed from both ends across a table. Great waves of rock forming, one after another, building on each other, layer upon layer, until the accumulated mass of folded stone begins to rise above the surrounding landscape. This is how the Himalayas were made. And the story of their making is one of the longest and most patient stories on Earth. Around 70 million years ago, the landmass we now call India was an island drifting northward across what was then a vast tropical sea called the Tethys Ocean. It was moving fast, as tectonic plates go. Over millions of years, the Tethys Ocean between India and the southern edge of Asia slowly closed, its floor subducting beneath Asia, until finally, roughly 50 million years ago, the two continents made contact. The collision has never really stopped. India is still moving northward, still pressing into Asia at roughly 5 centimeters a year. The crust between them has crumpled into the greatest mountain range the modern world has known, the Himalayas, which contain all 14 of the world's peaks above 8,000 meters, are the direct result of that collision. A collision that is still happening, right now, tonight, as quietly as everything else that lasts. And here is something that seems almost impossible, but has been confirmed by geologists who found the evidence at the highest places on Earth. Rock that formed at the bottom of a shallow tropical sea from the accumulated shells and skeletons of ancient ocean creatures. The summit of the world's tallest mountain was once a seafloor. When the first climbers to approach Everest's upper reaches noticed fossils in the rock, it must have been a deeply strange moment. Standing at the edge of the atmosphere, in the thin, cold air of the highest place a human being had ever been, looking down at the impression of a creature that had lived and died in warm ocean water, in a sea that no longer existed, in a world that was almost unrecognizably different from the one they stood in. The mountain had carried those fossils upward over tens of millions of years. It had lifted the floor of an ancient sea to the edge of space. That is what mountains do. They carry the past upward. There is something quietly comforting in that thought, if you let it settle. Everything that has been is not lost. It is simply carried somewhere else, transformed, lifted, changed in form but not erased. Mount Everest grows by approximately 4 millimeters every year. That is almost nothing. It is less than the thickness of a few sheets of paper. But it is not nothing, and it has been happening for a very long time. The mountain is still being made. It is, even now, becoming. Not all mountains are born from collision. The earth has other ways of making them, each one its own kind of quiet wonder. Some mountains are born from fire. When magma finds a path to the surface, through a crack, through a weakness in the crust, through a place where the pressure below has finally exceeded the resistance above, it emerges as lava and it builds. Each eruption adds another layer. Each flow cools and solidifies and becomes the foundation for the next. Over thousands of years, the accumulation of material forms a cone, and the cone grows, and eventually it becomes something that can be seen from a great distance, a mountain made entirely from what the earth has expelled from its interior. Mount Fuji in Japan is one of the most beautiful examples of this. Its near-perfect symmetrical cone, rising to 3,776 meters above the surrounding plains, is the result of centuries of eruptions layering basalt and ash and lava into a form so elegant it has been painted and photographed and contemplated more times than can be counted. Fuji is a stratovolcano, built from alternating layers of lava and volcanic ash, and it last erupted in 1707. It is considered dormant now, though not extinct. The fire is simply resting. And then there is Mauna Kea in Hawaii, which offers perhaps the most quietly astonishing measurement in all of geography. From sea level, Mauna Kea rises to 4,207 meters. Impressive, but not the world's highest. But Mauna Kea does not begin at sea level. It begins on the floor of the Pacific Ocean, some 6 kilometers below the surface. When measured from its true base to its summit, Mauna Kea stands approximately 10,210 meters tall. Taller than Everest. The world's tallest mountain is mostly hidden beneath the sea. There is something lovely in that. The thing that seems smaller on the surface is, in truth, the larger thing. What is visible is only part of the story. Mauna Kea was formed by a volcanic hotspot, a place where a plume of unusually hot mantle material rises through the overlying plate and melts through the crust. The Pacific plate has been drifting slowly over this hotspot for millions of years, and as it moves, the hotspot punches through in a new place, creating a new island, while the older ones drift away and slowly subside. The Hawaiian island chain is a record of that drift, each island older and more eroded than the last, stretching in a long arc across the Pacific like a trail of breadcrumbs left by a wandering fire. Other mountains are born from a different kind of violence. Not collision or eruption, but fracture. The Earth's crust is not uniformly strong. It has weak points, old scars, places where ancient stresses have left it more vulnerable to breaking than bending. When tension or compression forces act on these weakened zones, the crust can crack along fault lines and great blocks of rock can be displaced vertically. One block thrust upward while the adjacent block drops or stays where it is. The result is a fault block mountain, steep on one side, where the scarp of the fault is exposed and more gently sloping on the other. The Sierra Nevada range in California was formed this way. The great tilted block of granite that forms the range, with its dramatic eastern escarpment dropping sharply to the desert floor of the Owens Valley, and its gentler western slopes descending toward the Central Valley, is a fault block mountain on an enormous scale. The same process created the ranges and basins of Nevada and Utah, a landscape of alternating ridges and valleys formed by a crust being stretched and fractured, each range a separate block, tilted at its own angle to the desert sky. And there are mountains that are not new at all, but ancient beyond imagining. Mountains so old that the forces that made them are long gone. And what remains is only what erosion has left behind. The Appalachian Mountains of eastern North America are among these. They began forming more than 480 million years ago in a collision between ancient continental masses that no longer exist in any recognizable form. At their peak, the Appalachians may have been as tall as the modern Alps, sharp, dramatic, glaciated peaks rising thousands of meters above the surrounding landscape. But they have had 400 million years to be worn down, and what remains today is something softer and rounder, green and forested, the bones of a once great range showing through a covering of time. The Blue Ridge Mountains, the Great Smokies, the rolling ridges of Pennsylvania. All of them are the faded remnants of something that was once among the tallest structures on Earth. The Appalachians predate the dinosaurs. They were already old when the first reptiles appeared. There is something that moves in the chest thinking about that. The mountains we consider ancient are themselves the ruins of something more ancient still. Every landscape is a palimpsest, a page written over and over with older stories showing through beneath. A mountain, the moment it begins to rise, also begins to fall. This is not a sad thing. It is simply the nature of things, that what is built is also being unmade, and that the unmaking is as creative as the making. The material that wears away from a mountain does not disappear. It travels, it becomes something else. The forces that unmake mountains are patient and varied and utterly relentless. The most obvious is water. Rain falls on a high ridge and immediately begins its work. It seeps into the rock, finding the microscopic cracks and spaces, and when it freezes, it expands. Ice is larger than water, and the expansion exerts a force that can split stone. This process, called frost wedging, is one of the primary mechanisms by which rock is broken into smaller pieces. A boulder becomes a cobble. A cobble becomes a pebble. A pebble becomes sand. And the water carries it all downhill, eventually to a river, and the river carries it further, and eventually much of it reaches the sea. In the sea, it settles. Layer upon layer, the sediment accumulates on the ocean floor, compressed over millions of years into new rock, sandstone, shale, limestone. And if that seafloor is later lifted by tectonic forces, those sedimentary rocks become part of a new mountain, carrying within them the compressed remains of an older one. The mountain that was worn away becomes, in time, the raw material for the mountain that will rise. Nothing is lost. It is only transformed. Glaciers are perhaps the most powerful agents of mountain erosion. During the ice ages that have periodically gripped the Earth, glaciers advanced down mountain valleys, carving them into the characteristic U-shapes that are still visible in ranges like the Alps and the Rockies and the fjords of Norway. A glacier is not simply a mass of ice. It is a slow, grinding engine, dragging rocks and boulders along its base, scouring the bedrock beneath it, deepening valleys and sharpening ridges and carving out the bowl-shaped depressions called cirques that often hold the high mountain lakes so beloved by walkers. The Matterhorn in the Swiss Alps, that iconic pyramidal peak, was shaped by glaciers on all sides simultaneously, each one eroding its own face of the mountain until only the sharpest central ridge remained. A horn, in geological terminology, formed not by building up but by carving away. The Matterhorn is, in a sense, the last remnant of a much larger mass of rock, the rest of which has been ground down and carried away by ice over hundreds of thousands of years. And here is one of the most quietly counterintuitive things in all of geology, something that takes a moment to fully arrive. Erosion can make a mountain rise. The explanation lies in a principle called isostasy. The crust floats on the mantle below it, rather as a ship floats on water, and like a ship, it rises or sinks depending on how much weight it is carrying. A heavily loaded ship sits low in the water. Remove the cargo and it rides higher. The same is true of the crust. A mountain range is a heavy load and the crust beneath it is pushed down into the mantle by that weight. But as erosion removes material from the surface, the load lightens and the crust slowly rebounds upward, a process called isostatic uplift. This means that the very act of wearing a mountain down can cause its roots to rise. In the European Alps, researchers have estimated that erosion-driven isostatic uplift accounts for roughly half of the measurable rock uplift currently being observed. The mountain is being carved away at the top and rising from below at the same time. It is simultaneously diminishing and ascending. There is a kind of wisdom in that, if you want to find one. The things that are being worn down are not simply disappearing. Something deeper is rising. The Rocky Mountains of North America have their own complicated story of making and remaking. For a long time, geologists believed the Rockies were formed by a single tectonic event, a collision around 90 million years ago during what is called the Laramide Orogeny. But in 2023, a team of researchers at California State University Northridge, led by geologists Joshua Schwartz and Elena Miranda, published a study in the journal Nature Communications suggesting something more complex. Their research indicated that the Rockies were not formed in one event, but two, separated by roughly 50 million years. Two separate collisions, each contributing to the range we see today. What had seemed like a single story turned out to be a conversation between two events, each one building on what the other had started. This is how geology tends to work. The closer you look, the more complicated and more interesting the story becomes. Every mountain range is a palimpsest of events, each one layered over the last, the older stories still legible to those who know how to read them. The Great Smoky Mountains of Tennessee and North Carolina, those gentle, mist-covered ridges that give the range its name, erode at a rate of roughly 25 to 30 millimeters per 1,000 years. That sounds like very little, and over a human lifetime it is. But over the 400 million years the Appalachians have been eroding, that rate, applied consistently, would have removed an almost unimaginable volume of rock. The mountains that remain are a fraction of what once stood here. And they are still being reduced, grain by grain, in the fog and the rain and the slow work of time. There is a version of this that is not about loss at all. The material that was once a mountain peak in ancient Appalachia might now be sandstone in a cliff face in the Midwest, or limestone in a riverbed in Tennessee, or sediment on the floor of the Gulf of Mexico, slowly being compressed into rock that will, in some distant future, be lifted again by forces we cannot predict. The mountain does not end. It continues, changed in form, distributed across the landscape, becoming part of everything else. We have been traveling for a while now, a long way, through deep time, through the slow grinding of continents, and the patient work of ice and water, and the quiet rebellion of the crust rising back toward the light. You may have drifted already, and that is perfectly right. These words were never meant to be held on to. They were meant to move through the way a slow river moves through a wide valley, touching both banks and belonging to neither. If you are still here, still half listening, then perhaps we can rest a little longer in this place, this vast and ancient landscape of stone and time. Think, if it feels gentle, about the mountain nearest to wherever you are. It doesn't have to be a famous mountain or a particularly large one. It might be a modest ridge, a gentle hill, something that barely qualifies by any technical definition. Whatever it is, it has a story that goes back further than any human memory. It was shaped by forces that had nothing to do with human beings, and will continue to be shaped by forces that will have nothing to do with us. It is patient in a way that nothing human-made can quite be. It does not hurry. It does not worry. It simply continues. There is something in that which can be borrowed, if only for tonight. The Himalayas are still rising, 4 millimeters a year in the dark. The Appalachians are still slowly, quietly descending, their ancient peaks rounding further with every rainfall. Mauna Kea stands in the deep Pacific, most of its immensity hidden below the surface, enormous and unhurried. The mid-Atlantic ridge is spreading, a few centimeters at a time, creating new ocean floor in the dark water, the earth quietly making more of itself in the place where it is being pulled apart. All of this is happening right now. While the world sleeps, while you rest, the planet continues its deep and patient work. There is something about the scale of geological time that does something unusual to the sense of urgency we carry around. The things that felt pressing today, the things that sat heavy on your chest as you tried to settle, they are real, and they matter, and they deserve care, but they exist inside a story that is so much larger than they are. The geologists who study these processes spend their careers learning to think in millions of years. They develop what is sometimes called deep time intuition, the ability to feel, not just intellectually know, that the landscape around them is in motion, that what appears fixed is in fact fluid, that everything is in the process of becoming something else. People who develop this intuition often describe a particular kind of calm that comes with it, not indifference, but perspective. The recognition that change, even very slow change, is the natural condition of everything. You are, in a sense, a geological feature too. You are made of the same elements as the rocks, carbon and silicon and iron and calcium, assembled from the residue of ancient stars, shaped by the same forces of pressure and heat and time that shape the mountains, only on a much smaller and much faster scale. The calcium in your bones was once, in some unimaginably distant past, part of a seafloor not unlike the one that now forms the summit of Everest. The iron in your blood was forged in the heart of a star that died before the earth was born. You are ancient material, temporarily arranged in this particular form, resting in the dark on a planet that is still quietly making itself. That thought can be held very lightly. It doesn't require anything of you. It is simply something to let drift through, like a slow current of warm water moving through still air. The mountains outside, wherever they are, near or far, are doing what they always do. Standing, being worn, rising from within, carrying the past upward, releasing it grain by grain to the rivers and the sea. Everything that is made is also always being unmade. and in the unmaking, something new is always beginning. The Blue Ridge Mountains are still fading, slowly, into the gentle shapes they will carry for the next 100 million years. The Andes are still growing, fed by the slow descent of the Nazca Plate into the deep earth. Somewhere in East Africa, a rift is widening, almost imperceptibly, and in tens of millions of years it will be an ocean, and the land on either side will be two separate continents, and what is now a valley floor will be a seabed, and perhaps, in some unimaginable future, it will be lifted again into mountains that no human being will ever see or name. The earth is not finished. It has never been finished. It is always, in every moment, in the middle of its own long becoming. And so are you, in your own quiet way. Not finished, not even close to finished. Just resting, for now, in the middle of your own long story, while the planet turns and the mountains continue their ancient, unhurried work. The wind moves across the high ridges tonight. The snow settles on the upper slopes, where the air is thin and cold and very still. The rivers that begin in the glaciers are running in the dark, carrying their freight of dissolved mountain down toward the sea. And somewhere deep below the surface, the mantle stirs, and a plate shifts by a fraction of a millimeter, and the crust above it adjusts, and the mountain that will exist in 1,000,000 years is already, invisibly, beginning to take its shape. All of this is happening right now while you rest. You don't need to do anything with that. You don't need to hold it or remember it or turn it into anything useful. It can simply be there in the background, the way the mountains themselves are always there. Large and quiet and patient and old, asking nothing of you. The weight of the day has already begun to lift, the way a mountain's weight slowly lifts when the glacier above it melts. Something deep inside you is already beginning to rise. And so we leave it there, somewhere in the deep time, somewhere between the making and the unmaking, where the mountains are always quietly both. The day is far behind you now. Let it stay there. The stone is patient. The earth is turning, and you can rest now for as long as you need. Well, Alfred Wegener was not a geologist by training, and the established geologists of his day never quite let him forget it. He was a meteorologist, an Arctic explorer, a man more comfortable on an ice sheet than in a lecture hall. Perhaps that outsider's perspective was exactly what allowed him to see what the insiders had trained themselves not to notice. He looked at the map of the world and saw a puzzle that had once been assembled, then scattered. The fit between continents was not perfect, but it was close enough to be deeply suggestive, and Wegener spent years collecting evidence to support what his eyes were telling him. Identical fossil species found on continents separated by thousands of kilometers of open ocean. Rock formations that matched perfectly when South America and Africa were placed side by side on paper. Ancient glacial deposits found in tropical regions, suggesting those regions had once sat near the poles. His colleagues had explanations for each of these anomalies individually. They proposed land bridges now sunken. They proposed that animals had crossed the oceans on floating vegetation. Each explanation was possible in isolation. But Wegener looked at all of them together and felt, with a certainty he could not quite prove, that the simpler answer was the true one. Continents had moved. He died on the Greenland ice sheet on his 50th birthday in 1930 during an expedition to resupply a research station. His body was found the following spring, buried in the snow. He never knew that the world would eventually come around to his view. He never got to see the vindication that Marie Tharp's maps would bring decades later. But his idea survived him, the way the best ideas always do, not because he defended it, but because it was true, and truth, eventually finds its way through. Marie Tharp herself spent years in a kind of quiet, professional invisibility, her contributions to the mapping of the ocean floor often credited to others or simply overlooked. It was not until near the end of her career that her work received the recognition it deserved. In 1997, the Library of Congress named her one of the 4 greatest cartographers of the 20th century. She died in 2006 at the age of 86, having spent much of her life drawing a picture of a world that most people never see and rarely think about. The vast, mountainous, utterly dark terrain of the ocean floor, where some of the most dramatic geography on Earth lies hidden beneath kilometers of cold water. The mid-ocean ridge system that Tharp helped reveal is the longest mountain range on Earth. It stretches for approximately 65,000 kilometers, winding through every ocean basin like the seam of a baseball. Most of it lies 2 to 3 kilometers below the surface. Almost none of it has been seen directly by human eyes, and yet it is where new ocean floor is constantly being born, where the Earth is most actively making itself, where the deep, creative work of the planet proceeds in complete and permanent darkness. There is something quietly moving about that. The most generative place on Earth is the least visible. The greatest making happens when no one is watching. The story of the Himalayas contains within it another story, smaller and stranger, that is worth pausing over. In 1852, a Bengali mathematician named Radhanath Sikdar was working in the offices of the Great Trigonometrical Survey of India in Calcutta when he made a calculation that stopped him in his tracks. He had been working through a set of observations made of a distant peak in the Himalayas, a mountain then known only by its survey designation, Peak the 15. The measurements had been taken from multiple stations across the plains of India, each one hundreds of kilometers from the mountain itself, and the mathematics of triangulation had been used to determine the peak's height from those distant observations. Sikdar ran the numbers. Then he ran them again. He walked into his supervisor's office and said, with characteristic understatement, that he believed he had discovered the highest mountain in the world. The mountain was later named for Sir George Everest, the Surveyor General of India, though Everest himself objected to the honor. He pointed out that his name could not be written in Hindi or pronounced easily by the local people, and he felt the mountain deserved a local name. His objections were overruled. The mountain carries his name still, though in Nepal it is called Sagarmatha, meaning goddess of the sky, and in Tibet it is called Chomolungma, meaning goddess mother of the world. Both of those names feel somehow more appropriate to the thing they describe. The survey that produced Sikdar's calculation was one of the great scientific undertakings of the 19th century. The Great Trigonometrical Survey of India involved decades of painstaking measurement across the entire subcontinent, using enormous theodolites that sometimes had to be carried by 12 men at a time, establishing a network of precisely measured triangles that gradually extended northward toward the highest mountains on Earth. The men who carried out the survey worked in extreme heat and extreme cold, through monsoons and across deserts, many of them dying of disease or exhaustion before the work was complete. The accuracy of their final measurements, given the instruments available to them, was remarkable. Sikdar's calculated height for Everest was 29,002 feet. The currently accepted figure, measured by GPS and satellite in 2020, is 29,032 feet. The 19th century surveyors, working with brass instruments and logarithm tables, were off by 30 feet. 30 feet, over 29,000. There is something about that precision, achieved under such difficult circumstances, by people working with such limited tools, that is worth sitting with for a moment. The care that went into it. The patience, the willingness to do a thing slowly and carefully and well, even when no one was watching, even when the reward was a number in a table that almost no one would ever read. The Tibetan plateau that surrounds the Himalayas from the north is itself one of the most extraordinary features of the planet's surface, averaging more than 4,000 meters above sea level across an area roughly the size of Western Europe. It is sometimes called the roof of the world. A vast, cold, windswept upland that was itself lifted by the same collision that raised the Himalayas. The plateau is so large and so high that it affects the climate of the entire Asian continent, deflecting the jet stream, driving the monsoon, creating the weather patterns that determine when rain falls and when it does not across a region home to billions of people. They are climate engines, shaping the conditions under which much of humanity lives. And beneath the plateau, the Indian plate continues its northward push, pressing against the underside of Asia, thickening the crust to almost twice its normal depth. The roots of the Himalayas extend as far downward into the mantle as the peaks extend upward into the sky. For every meter of mountain that rises above the plateau, there is a corresponding depth of crustal root below, pressing down into the hot mantle like the keel of a very slow and very heavy ship. The Hawaiian hotspot that created Mauna Kea and the other Hawaiian islands has been active for an extraordinarily long time. Now mostly submerged seamounts, worn down below sea level by erosion and subsidence, are around 80 million years old. The Big Island, where Mauna Kea and Mauna Loa stand today, is the youngest, still directly over the hotspot, still being actively built. Kilauea, one of the most continuously active volcanoes on Earth, has been erupting almost without interruption since 1983. New land is still being added to the island, lava flowing into the sea and solidifying into new rock, the island slowly growing at its edges, while the volcanoes at its center build higher. The native Hawaiian people have lived alongside this volcanic activity for more than 1,000 years, and their traditions reflect a deep familiarity with the living, changing landscape. Pele, the Hawaiian goddess of volcanoes, is understood not as a destroyer but as a creator. The lava she sends forth is not an ending but a beginning, new land being born from fire, the island extending itself into the sea. The Hawaiian Islands exist because of volcanic activity. The soil that makes them fertile, the land that makes them habitable, the very ground beneath every living thing on those islands, all of it came from below, from the heat and pressure of the mantle, expressed through the patience of repeated eruption. The summit of Mauna Kea has its own particular significance, quite apart from its geological story. Because of its height, its distance from city lights, and the stability of the atmosphere above it, Mauna Kea hosts some of the most powerful astronomical observatories on Earth. On a clear night, the scientists working at those observatories look outward through air so dry and still that the stars barely twinkle, their telescopes gathering light from galaxies billions of light years away. The summit of a volcanic mountain that began on the floor of the Pacific Ocean is now one of the best places on Earth from which to observe the rest of the universe. The Sierra Nevada, that great tilted block of California granite, has its own quiet story of ancient fire. The granite that forms the range was not always near the surface. It formed deep underground, During a period of intense volcanic activity, roughly 100 to 200 million years ago, when magma intruded into the roots of an older mountain range and cooled very slowly over millions of years into the coarse-grained crystalline rock that now makes up El Capitan and Half Dome and the other iconic formations of Yosemite Valley. What is now the surface of those granite walls was once kilometers underground. It was brought to the surface by the erosion of the overlying rock and the uplift of the fault block. A long, slow journey upward that took tens of millions of years. Half Dome, that distinctive rounded face rising above the Yosemite Valley floor, has a shape that is sometimes assumed to be the result of a glacier cutting it in half. But geologists have established that its form is primarily the result of a process called exfoliation. The slow peeling away of curved sheets of granite as the overlying rock is removed and the pressure on the granite below is gradually released. As the weight above decreases, the granite expands, and the expansion causes curved fractures to develop parallel to the surface. These sheets of rock peel away one by one over thousands of years, leaving the smooth, rounded surface that climbers now ascend and that walkers stop to photograph from the valley floor. Half Dome was not carved. It was gradually revealed as the rock around it and above it was stripped away, leaving the harder core standing alone. The Appalachians offer one more detail worth lingering over. Beneath those ancient, rounded mountains, geologists have found evidence of a supercontinent that existed before Pangaea. A still older assemblage of landmasses called Rodinia, which began to break apart roughly 750 million years ago. The Appalachians themselves are partly the product of the collisions that assembled Pangaea from the fragments of Rodinia, and they carry within their rocks the chemical signatures of ancient ocean floors and volcanic arcs that have long since disappeared. Reading the Appalachians is, in a sense, reading a history of the world that stretches back 750 million years. A history written in stone, patient and legible to those with the training to understand it, folded into the gentle green hills that many people drive through without quite noticing. The rivers that flow from mountains are themselves remarkable instruments of erosion, and the way they work is worth pausing over, because it is another one of those processes that seems impossibly slow until you begin to understand the timescales involved. A river carrying sediment downstream is not simply transporting material passively. The sediment it carries acts as a tool, grinding against the riverbed, wearing it down. The harder and more abundant the sediment, the faster the erosion. In steep mountain rivers, where the gradient is sharp and the water moves quickly, this process can cut through rock at rates that seem, in geological terms, almost rapid. The Colorado River has carved the Grand Canyon, more than a mile deep, up to 18 miles wide, in roughly 5 to 6 million years. That is a short time, geologically speaking. The rock it cut through is vastly older, in some places nearly 2 billion years old. But the river, given enough time and enough gradient, was patient enough to reach it. The Grand Canyon is perhaps the most famous geological cross-section in the world. A place where the layers of the Earth's history are laid out in visible sequence, each stratum a chapter in a story that begins in the deep Precambrian and works its way forward through 500 million years of accumulation. Walking down into the canyon is, in a literal sense, walking backward through time. The rocks at the rim are around 270 million years old. The rocks at the bottom, the dark Vishnu schist of the inner gorge, are approaching 2 billion. Standing at the river and looking upward at those walls, you are looking at a span of time almost too large for the mind to hold. John Wesley Powell, the one-armed Civil War veteran who led the first recorded expedition through the Grand Canyon in 1869, wrote about the experience with a mixture of wonder and something approaching reverence. His small party of men descended through the canyon in wooden boats, running rapids that had never been mapped. camping on sandbars beneath walls of stone that rose hundreds of meters above them. Powell was a geologist as well as an explorer, and he understood, better than most of his companions, what he was looking at. He wrote that the river had been the instrument of its own valley's creation, that the canyon was, in a sense, the autobiography of the river, written in stone. That image has stayed with geologists and writers ever since, the river writing its own story in the landscape it moves through, the land as text, the water as author, the canyon as a sentence that took 5 million years to complete. Wind, too, is a sculptor of mountains, though it works more gently than water and ice and is most visible in arid landscapes where vegetation does not protect the rock from its action. In the desert ranges of the American Southwest, wind-blown sand has carved the rock into forms of extraordinary variety: arches, hoodoos, balanced rocks, hollowed alcoves in cliff faces. These formations are not the work of a moment. Each one represents thousands of years of patient abrasion, grain by grain, the wind carrying its tools of sand and dust and pressing them, hour after hour, against the exposed surfaces of stone. The hoodoos of Bryce Canyon in Utah, those pale spires of eroded limestone standing in their thousands on the canyon rim, are formed by a combination of frost wedging and rain erosion acting on rock of varying hardness. Where the rock is harder, it resists erosion and forms a cap. Where it is softer, it erodes faster, and the spire beneath the cap is gradually narrowed until the formation looks like a figure wearing a hat, standing in a crowd of other similarly hatted figures, all of them slowly, silently diminishing. A hoodoo that stands today will not stand in 10,000 years. Its cap will fall, its spire will crumble, and the material that was once a pale tower in the Utah desert will become sediment in a river, and eventually, perhaps, part of a new layer of rock somewhere downstream. The chemical weathering of rock is another process that is easy to overlook because it is entirely invisible. Rainwater is slightly acidic. It absorbs carbon dioxide from the atmosphere as it falls, forming a weak carbonic acid. When this mildly acidic water contacts certain types of rock, particularly limestone, it dissolves them. Slowly, over thousands of years, the water finds its way into cracks in the limestone, widening them, dissolving the rock from within, creating passages and chambers that grow larger with each passing century. This is how caves form. Not by collapse, but by dissolution. The rock being quietly eaten away by chemistry, leaving behind hollow spaces that can grow over millions of years into vast underground systems. The Mammoth Cave System in Kentucky, the longest known cave system in the world, extends for more than 650 kilometers of mapped passages, and new sections are still being discovered. All of it was created by slightly acidic water working through limestone over the course of several million years. The stalactites and stalagmites that decorate some of its chambers are themselves the product of the same chemistry in reverse. Water carrying dissolved calcium carbonate dripping from the ceiling and depositing its mineral load. Drop by drop, building structures that can take 100 years to grow a single centimeter. A stalactite that reaches a meter in length may represent 10,000 years of patient accumulation. The mountain, in all its forms, is never static. It breathes in geological time. It rises and falls and dissolves and reforms and is carried away and deposited and lifted again. The same calcium that was once a reef in a shallow sea becomes the cliff above a river, becomes the sediment in the river's bed, becomes the new rock in a distant formation, becomes, in some unimaginable future, part of a mountain that has not yet begun to rise. The cycle has no beginning and no end that we can identify. It simply continues, patient and vast, and entirely indifferent to whether anyone is watching. And yet here we are watching, wondering, finding something in all of this immensity that feels, strangely, like company.